Hi there, Mr. Sutton here, bringing you the AB Calculus 612 Extra Practice Number 3 solutions on area between curves. For this problem, we're just trying to find the area enclosed by the f of x and g of x curves. This is a calculator question, so let's take a minute to graph these and see what we're looking at. So in my y equals, I've entered f of x as y1, g of x as y2, and I'm not really sure what window to use on these, but it probably isn't too far from the origin, so let me just do zoom 6, and we'll see what we get. So there's f of x, and there's g of x. So, I mean, the intersection, it looks like, is going to happen between, say, negative and positive 3. So let me just adjust my window so I can see that a little bit better. So let me do negative 3 to positive 3, and then zoom fit this thing, zoom 0, and we'll get an even better picture of what's going on. There we go. Now I can see pretty clearly. So we have something that looks like this. And if we just do intersect here, second trace, option 5 for intersect. Let me see where we're crossing. I have a hunch it's negative and positive 2, but let's just be sure. So enter, enter, enter. It's negative 2 on the left side. And let me do second trace, option 5 again. Move my spider over to the other intersection. And press enter 1, 2, 3 times, positive 2. Okay, so we can see that f of x equals g of x at plus or minus 2. So then to find the area between these curves, we're going to do, let's see here, the integral from negative 2 to positive 2 of, and now we have to do top minus bottom if we want to avoid using absolute value. So this top function here was f. It's the one that had the y-intercept of 6. Bottom function was g. So we're just going to do f minus g of x dx and plug that in the calculator. So to do this on the calculator, let me just do, let's see, math 9 for integral. We've got negative 2 there. There we go. And positive 2. And now we're going to do, let's see here, alpha trace y1 because the f function comes first, and then we're going to subtract the g function, so that's alpha trace y2, and I'll put an x there for dx. Press enter. Comes out to 21.333. For this problem, we're trying to find the area of the region enclosed between f of x equals sine of x and g of x equals 2 sine of x, but just on the interval from 0 to 2 pi, otherwise we could be playing this game forever. Let me start by graphing these out. So I've entered f of x as y1, g of x as y2, and for my interval, well, let me just use the window they gave me, 0 to 2 pi. So let me do window 0 is my x min and 2 pi, my x max, and we'll do zoom fit, zoom 0. So here's our two functions. Here is f of x, your typical sine curve, and here is g of x, basically the sine curve but with a higher amplitude. So now we're just looking at the area between these two curves. Now in order to find this area, this is a little bit trickier because initially g is the higher up function, so you would be doing g minus f, but over here they switch, and now f is the higher up function. So in order to really make this happen, what we're going to have to do is either split this up into two integrals, and it looks like pi is where we would have to switch, or you could be a little bit more clever about it and do one integral from 0 to 2 pi, but put an absolute value around the two functions when you subtract them, so that we always just end up getting a positive version of whatever that difference is. So I'm going to do that version because I am using a calculator, so I can just let my calculator figure it out. So I'll have absolute value of f of x minus g of x dx, and let me make that happen on the calculator. So I'm going to do math 9 for integral. We're doing 0 to 2 pi. And in here, let me do, let's see, alpha window is going to let me get absolute value out of that menu. And now I'm going to do y1 minus y2 because that's where I stored my two functions. Just taking a quick look here. Again, sine of x was y1, 2 sine of x, that was the g function, was y2. So let me just go back into my absolute value here. We do alpha trace y1 minus alpha trace y2 dx. And let's see what all that comes out to. Yeah, exactly 4. Sweet. On this problem, I want to find the area enclosed by sine of x and x squared. So I'll start by graphing these out. So on my calculator, I'm storing sine of x as y1 and x squared as y2. And I'm not really sure what window I should use, so let me just do zoom 4, because I don't think it's going to take too long for these things to overlap. So we've got this little sliver in here, and I'm actually going to zoom in a little bit more. Let me adjust my window. I'm going to make my window go from negative 0.5 to positive 1.5, because I really don't need a whole lot of left-right window in order to get this thing. And then we do zoom 0. So zoom fit. So there is my sine function. There's my x squared. So yeah, we're trying to get this space in here. Okay, well, in order to get that, I need limits of integration. They clearly intersect at 0. If you plug 0 in for x on both of these, you get 0 back. But what is this other intersection point? So in order to solve this, I'm going to have to use the intersect function on the calculator. So I can see that f of x equals g of x at, and let's go back to the calculator to see exactly where that is. Let me do second trace, option 5 for intersect. And then let's go over here and press enter a couple times, 3 times actually. 1, 2, 3. And that intersection point is about 0.8767 if I round that off to 4 decimals. So I'm going to store that actually. So we intersect at 0, of course, and at this other point, this 0.8767. I am going to refer to that hereafter as p, just so I don't have to keep writing that gnarly looking decimal. And on my calculator, I'm actually going to follow suit and store it as the constant p. So I'm going to just quit out of here. I'm going to go to store, and that immediately takes the x-intersection, the intersection x value that I just found, and stores it wherever I want. And I'm going to do, let's see, alpha p. I just kind of like p when I'm dealing with areas and volumes. So now I can just pull that back whenever I need it. And all I need now is the integral of the difference between these functions. So I have the integral from 0 to p of, and if I want to avoid absolute value, I have to do top minus bottom here. So the top function in this interval anyway is going to be our sine function, and then x squared is this concave up underneath function. So we're going to do f of x minus g of x dx. And let me go back to the calculator for that. So I've got math 9 for integral. We're going from 0 to p. And then I'm going to do, let's see, this is going to be y1 minus y2 the way I've got it set up. So alpha trace y1 minus alpha trace y2 dx, and enter, giving us 0.136 for our final answer. For this problem, I want to find the area of the region enclosed by these two curves. Let me start by graphing them out. So here I am in my y equals. I'm entering my f of x function as y1, and y2 is going to be the g of x function. I'm not really sure what window to use, so let me just go with zoom 6. That's 10 in every direction. I'm bound to see something out of that. So we've got this little region right here. I'm going to zoom in a bit on that. Let me go with zoom 4. Get a better picture of that. So I just need to find the area in here. So I need to know what these intersection spots are. Those will be my limits of integration. And then I'm just going to do top minus bottom, which is going to be, this is the line g of x. So this is going to be g of x minus f of x inside my integral. But first things first, limits of integration. So I need to figure out where f of x equals g of x. So going back to the calculator, I'm going to have to do, let's see here, second trace, option 5 for intersect. And let me find this one on the left side first. So where'd my spider go? There he is. So I'll press enter 1, 2, 3 times to get that. And that is about negative 1.2207. Now I'm actually going to store this as the letter P. I'm going to write this on my paper so I can say P instead of saying this decimal. I'm also going to do that on my calculator. I'm going to quit out of my graph screen, and I'm going to press the store button to store my X value that I just found, and we'll store that as alpha P, or whatever letter you want. I go with P this time around. So now we have to go back to the graph. There's our graph, and I'm going to find this other intersection spot. So second trace, option 5 for intersect, and move my spider over to that spot. Press enter 1, 2, 3 times. That's about 0.7245. I'm going to call that point Q. And again, I'm going to go on my calculator and store that value. So escape out of there. Now I'll press the store button and I'll do alpha Q. So now all I have to do is take the integral from P to Q of, we said it was going to be g of x minus f of x dx. And I can do that whole thing on my calculator at this point. So here's what this does look like on my calculator. I have my integral, which I got with Math 9, alpha p, alpha q, those are my limits of integration. And we stored the g function as y2, the f function was y1, and then I always put x for the dx. Press enter, and it's about 1.846 if I go to 3 decimals. For this problem, we have some regions bounded by the graphs of y equals 4x, which is the line here, and this other function, this cubic function. We want to know the sum of the areas of these shaded regions. So in order to figure this out, I'm going to need to integrate the difference of the two functions. And because the top versus bottom function changes about halfway through, I'm just going to use absolute value around my integrand when I do this. Before I can even do that, though, I need my limits of integration. I need to figure out where 4x and this polynomial here intersect. So let me start by labeling these things, just so I don't have to keep rewriting these functions. I'm going to call this first one f of x, and this other one I'll call g of x. So I want to figure out where f of x intersects g of x. And this is a calculator problem, so I'm going to do this on the calculator. So in my y equals, I put in this 4x1 as the y1, and for g of x, that's in y2 now. In terms of a window to graph these in, well, they already gave me the graph, basically. I just need to get it in my calculator. So it looks like they're using a window of maybe like negative 1.5 to 2.5. Something around that should do the job. So let me go to window. And let's see here, negative 1.5 be my x min, and for my x max I'll do 2.5, and then zoom 0, zoom fit. So there's my 4x line, and here's the cubic function. So let me do second trace and option 5 for intersect. I want to figure out the leftmost intersect, which is all the way back here. So let me press enter 1, 2, 3 times, and that is about negative 1.3028 if I round that off. Now I'm going to name that P just so I have something to quickly refer to it as, and I don't have to keep rewriting this number. I'm also going to store that as P on my calculator. So let me quit out of there, and I'm going to go to the stow button, and I'll store that as alpha P. So now I can pull that up whenever I need to. And let me find the other intersection point. So we'll do second trace, option 5 again. And let me move my spider over to the far right, over to this spot right here. And it's a long journey. It's an adventure of sorts. And my spider made it over there, so let me do enter, enter, enter. That's about 2.3028. And I'm going to call that point Q, or at least the x value Q. As you might imagine, I'm going to go ahead and store that on my calculator as well. So let me quit out of there and store that answer as alpha Q. All right, press enter. All right, so now I can easily pull up those numbers and I'll get the exact values rather than some rounded off version. So what I need to do here again is I need to take the integral of basically top minus bottom, but again, because the bottom and the top are changing, I've really got a choice here. I could either split this up into two integrals, and in the first one I could do, let's see here, this would be g minus f, and in the second one I could do f minus g. But a quicker way to do it, since I do have a calculator, I'm just going to do the integral from p to q, so from here all the way to here, and I'm just going to use absolute value. And then if I use absolute value in here, it doesn't matter if I'm doing f minus g or g minus f. Either way, all of my distance strips are going to come out positive and just give me the area rather than counting negative area. So let me go ahead and do this on the calculator. So here we are again, just to show you how I'm entering this in. I'm going to do math 9 for integral, and then I'm doing alpha p and alpha q as my limits of integration. In here, I need the absolute value, so I'm going to do alpha, and then window pulls up a menu that has abs on it, so I'll just press enter for that abs, absolute value. Inside here, I stored f as y1 and g as y2, so I'll do alpha trace and pull up y1, and then we're going to subtract alpha trace y2. And let me put x over here next to the d, press enter, and that comes out to roughly 6.083, giving us answer choice C. For this problem, we're given the regions bounded by the graphs y equals 6x and y equals 5x squared minus x cubed. We've got these shaded regions. Basically, we're trying to find the area of those shaded regions. And we're told that these graphs intersect at 0, 2, and 3, which is good because we don't have a calculator to verify this. So we want to know which expression would give us the sum of those areas of the shaded regions. So in general, if you're trying to find the area between two curves, the idea is you're taking the integral from the left intersection to the right intersection, and then you're doing a top minus bottom, at least if you're trying to avoid using any kind of absolute value symbols. So taking a look at what we've got here, we're going to need two integrals, because if you look at what's happening in this graph, the function that's higher up is changing at around x equals 2. So we can't use one integral and still hope to avoid getting negative area. We want to get all positive area when we do this, so we always want to be doing top minus bottom. So I notice from the interval from 0 to 2, the 6x function is greater than the 5x squared minus x cubed function. So 6x is the top function on that interval. And on this other interval from 2 to 3, the 5x squared minus x cubed is greater than the 6x function. So this is going to determine what I write in my integrals here when I split this up. I'm going to have one integral from 0 to 2, and since I always want to do top minus bottom, I'm going to do greater minus lesser, so 6x minus 5x squared minus x cubed dx. And I'm going to add that to another integral from 2 to 3. For that one, I'm going to have to do 5x squared minus x cubed minus 6x. Again, I'm just trying to do higher minus lower. And looking at my answer choices, it looks like this is going to match answer choice B. For this problem, the regions bounded by these two graphs up here are shaded above. We want to know which of these expressions gives us the sum of these shaded regions. So in general, we're trying to take the integral from left to right of top minus bottom. That's how we get that area, and it's how we get it to be positive area rather than negative area. We just want to get positive area here. So on a problem like this, where your top function is changing kind of halfway through the problem, you can't use just one integral, because if you just try to use one integral from negative pi over 2 to pi over 2, then, I mean, half the time you're going to be getting positive area, the other half of the time you're going to be getting negative area, and those are going to kind of cancel out, and you're not going to get the actual area contained inside those shaded regions. So to make sure that we're always doing top minus bottom, you're going to need to split this up into two integrals, at least if you're trying to do this without absolute value, which if you look at the answer choices, there's no absolute value involved. So we need to do top minus bottom for the first interval from negative pi over 2 to 0, where those things intersect. It looks like the function y equals 2x over pi, which is a line essentially, that's going to be greater than sine of x. So 2x over pi is the top function. And then on the other interval from 0 to pi over 2, it looks like sine of x is higher up. So my first integral from negative pi over 2 to 0, that's going to be 2x over pi minus sine of x dx. Again, top minus bottom. But then because things are switching up for the next integral from 0 to pi over 2, and I'm going to be adding these integrals here, then I have to do the higher function sine of x minus 2x over pi dx. So that's going to match, let's see, which answer choice? It's looking like answer choice C. D had the basic idea but did things backwards. For this free response problem, on which I cannot use a calculator, we have this R region bounded by the graph of this crazy looking function, the x-axis, and the vertical line x equals 4. First task is just to find the area of R. So in general, we're going with the integral from left to right, top minus bottom. Now left to right here, we're going from, it looks like 1 to 4 for the limits of integration. And top minus bottom, well, the bottom function is just y equals 0. So really, we're just taking the integral of this function here from 1 to 4. So to do that, I'm actually going to take this 3 out of the function to start with, or take it like out of the integral. So I have 3 times the integral from 1 to 4. And inside, I've got x minus 1 divided by radical x. To make that a little bit easier to take the antiderivative, I'm actually going to divide both of these terms by radical x and rewrite it with a single exponent. So x over x to the 1/2 essentially is going to be x to the 1/2 power. And then negative 1 over x to the 1/2 is going to be negative x to the negative 1/2. And we have a dx in there still. Now I'm going to use my reverse power rule. So going left to right, this 1/2 bumps up to a 3/2, and we're multiplying by 2/3. So we have 2/3 x to the 3/2 power. We still have this 3 out in front, by the way. Don't want to forget about that. Now moving on here, this exponent bumps up to a positive 1/2. Dividing by that, we're actually multiplying by 2, so I have minus 2x to the 1/2. Evaluating all of this from 1 to 4. And now let me plug a bunch of stuff in. So I've got a 3 on the outside, or actually I'll make that a 6, because these both have 2's, so I'm going to factor out a 2 to multiply by the 3. So I've got a 6 out there. Inside I still have a 1/3, and I just have a 1 for the coefficient now on the x to the 1/2. So inside then, I'm going to have 1/3 times, and this is going to be, let's see here, square root of something to the 3rd power. So I'm going to plug 4 into that, and I'm also going to have just the square root of 4 over here. So I have 1/3 square root of 4 cubed minus, this is going to be square root of 4. So that's everything with 4 plugged in. Now I'm going to subtract everything with 1 plugged in. So I'm going to have a 1/3 square root of 1 cubed minus square root of 1. Cleaning up the stuff inside here just a little bit. Square root of 4 is going to be 2. Cubing that gives me 8. So I have 8/3. I still have that 6 out there. 8/3 inside. We're subtracting 2. And over here, this is just going to be minus 1/3 plus 1. Cleaning up a little bit more, we have, let's see, 8/3 minus 1/3 is 7/3. We also have a negative 2 and a 1. That adds up to negative 1. So 7/3 minus 1, that's really 7/3 minus 3/3, which is going to be 4/3. So we have 6 times 4/3. 6 divided by 3 is 2. 2 times 4 is 8. So 8 is our final answer when all is said and done. You actually could have stopped back here before you started simplifying, but hey, we had a good time, right?